Good evening, everyone. It's so lovely to have you all here with us. I'm Satvika from Sigma Sai, and I'll be your host. Now, have you ever been curious to know what building a rocket is like? Rocket science is a term generally used to describe something that is very difficult to understand. Let's explore and find it ourselves. Today, we have with us Kinit Sai, our speaker for the event. He is here to help us all get well versed in the realm of rocketry and satellites and take us through everything from the basics of building model rockets to the world of satellites and the breakdown of their mechanisms. This session will be followed by a Q&A round where all of your questions will be answered. So without any further ado, let's dive right into the world of rocketry and satellites. Over to you, Kenneth.
Hi, I'm Kenneth, and I'll be taking you guys through our session at Astra. So, you all must have heard the phrase, it's not rocket science. Well, this is definitely used to describe something very complex and complicated. So, let's dive right into why this phrase is being phrased as such. So, what are rockets and satellites? Well, rockets are the vehicles or tools which have the capability of taking an object, generally a payload, and in some cases even humans, into space beyond the atmosphere or a certain apogee in the atmosphere using a rocket engine. Whereas a satellite can be a natural or a man-made object that's revolving another bigger object or a planet. As such, which we know many satellites orbit Earth, which are made by man itself. So, rockets are basically classified into three different categories based on the type of fuel they use. That is, solid, liquid, and hybrid. The most general case used ones are liquid, but one of the most efficient and easy to use ones are the solid. Solid fuels, as the term suggests, have solid fuel inside them. That means that it has complete solid makeover, whereas hybrid is a combination of both solid and liquid, where the fuel is in the form of a solid, uh, whereas an oxidizer is in the form of a liquid in a pressurized chamber, where a liquid engine has both oxidizer and fuel in liquid phase. The general cases of solid fuel is HTBP, whereas for liquid there are many varieties coming from um, liquid hydrogen and liquid oxygen engines to liquid oxygen and liquid kerosene engines. So, are there any other classifications based upon the rockets which are generally used? Well, yes, there are. So, basically, there are two more categories in which rockets are generally seen based upon, um as you can see in your screens, those are sounding rockets and orbital rockets. Sounding rockets suggest that they don't cross the atmospheric boundary of the Earth, whereas orbital rockets cross the boundary and deliver their payloads to certain orbits, as we shall discuss further. So basically, these two can be distinguished very easily. As you can see, the difference between a sounding rocket and an orbital rocket, where sounding rockets are in the atmosphere, so they require most control over them. So they cut through the atmosphere as for the pointy nose cone and the fins for control surfaces. Whereas an orbital rocket doesn't have any fins and it has a blunt nose cone to withstand much higher pressures in the atmosphere. So, are there any more types than these general ones? Well, there certainly are. And these are one of the most researched areas at present. Those are plasma and ion based propulsion systems. And these are one of the most exciting fields where you can research upon right now. So, I guess everyone has been waiting to take a dive into what a rocket comprises of. So, a rocket basically comprises of four functional levels, that is, structural, propulsion, payload, and guidance. So, starting with the structural components of a rocket generally comprise of the nose cone, fins, and the framework that comprises all the other functional levels as we shall be discussing. This provides the structural integrity to the rocket and also gives the ability to withstand great pressures. Propulsion. Propulsion is the key part of a rocket, where it propels the rocket to the beyond the atmosphere, which comprises the fuel tank and the main rocket engine. Payload. This is one of the most key elements and one of the most important elements, as it contains any kind of satellite, experimental payload, or one of the most important things, humans. So we have these three systems which are in a rocket. So what guides them? So basically, this guidance system maintains the control over the rocket, where it has to go, the path it has to follow, the trajectories, etc. So guidance system is one of the most key elements of a rocket, which tells everything for a rocket what to do and how to do. Now, how does a rocket work? Basically, these four systems which we discussed go hand in hand, where the guidance system tells the rocket what to do at what point. As the countdown approaches, the rocket engine fires up and starts to generate the thrust. Now, once the thrust reaches a certain point where it's able to counteract the weight of the rocket, we have liftoff, beyond which the rocket guidance systems guide the rocket to its destination. Now, if you guys observed something, as a rocket propels forward towards the atmospheric boundary, fuel is continuously burnt, which causes a lot of dead weight. By dead weight, I mean as the rocket fuel is burnt along with the oxidizer, the containers where this fuel has been uh, where this fuel has been pressurized is being emptied. So as they keep emptying, the fuel tanks become redundant. So many of the spacebound rockets, they use something known as staging. So as you can see, this space shuttle over here with these two rocket boosters. So as it reaches a certain altitude, the rocket boosters don't have enough fuel in them. So they are jettisoned, meaning they are just separated from the main rocket. Now, also, as we discussed in these four categories, there are a lot of things in which active research is happening around the world. One of the key most things for a structural part is the isogrids. Isogrids are the parts of the structural framework, the plates which cover the rocket. These are generally very heavy. To counteract the weight, something known as isogrids take place, where a certain pattern of triangles and rectangles and shapes are generally used to optimize the structure and to bear the load for the minimal amount of weight that it contains. The other part is in propulsion, where new kind of fuels are being discovered, where ion propulsion and other propulsion systems are being worked upon. There are other guidance systems where you can see this gyro system, which is used to maintain the stability of the rocket. Can is a old model one, and it's there are more research opportunities which can happen over here as well. And one of the most leading and innovative kind of launch system and is being worked upon by Spin Launch, where they have an vacuum chamber where they spin the rocket continuously, and upon reaching a certain velocity, it's released. And this is a key point where you guys can definitely take a note for research. So we have discussed a lot on structural, etc., and a lot more things. So let's take a dive into something much more important for a rocket. That's engines. So you guys must have seen many rockets which have their engines running, and they have this very bright red flame coming from behind them. Have you ever wondered why don't they melt? They generally reach a temperature of around 3500 Kelvin. That's more almost half the surface, half the temperature of the surface of the sun. And that's a temperature enough to not only melt any substance but vaporize them. So what prevents them from melting? What and especially the nozzle, which contains the all the combustion and directs the pressure, directs the thrust. That's something that we shall take a deeper dive into. So first, one of the key things where we can use this um heat sinks. Heat sinks are basically, as the sound suggests, convection of heat, where one material is very close to the surface of the flame, which is taking the full blast of the heat. And this material is able to actively conduct the heat away from the center. Now, as it conducts away the heat, it also has a certain limit. Now, as you can see, this rocket engine, where we have the main combustion chamber, the nozzle, and the throat. So now, this walls of the rocket engine are can be made in thick enough to actively convect the heat away from the center, thus preventing the meltdown of the surface directly in contact with the flame. But this also generates an issue where this rocket thrust, which the flames are providing, the temperature is so high that we can only convect a certain amount of heat. So that itself brings a limiting factor into our engine, where heat sinks can only have a certain limit. So as this heat sinks generate are convenient enough, they also have bear a lot of weight into them, where our rocket needs to be very light so that we can provide the maximum payload into the orbit. So this is why these kind of systems are used for small scale reaction control systems, which have pulsed engines. They only run for a short burst of a second to provide a certain thrust. So the active convection of heat can be utilized. Now, the another method for cooling a rocket engine is by using the fuel oxidizer ratio. Now, whenever you have two certain fuels, a fuel and an oxidizer, they have to combust at a certain temperature. Now, this is where I'm sorry, someone has unmuted. Can you mute yourself? All right. So, coming back to our discussion. Now, when you have a fuel and oxidizer mix, they react best at certain ratios, known as the stoichiometric ratio, where the combustion for the quantity of fuel and oxidizer is perfect, and for each and every atom of fuel, there's an oxidizer pair. This generates the maximum amount of heat in an engine, and this can also generate so much heat that it can melt down the engine. So, for most general case scenarios, this stoichiometric ratio is avoided. The engine is either at fuel-rich or oxidizer-rich state, where the combustion takes place. Now, as a rocket engine is very fuel-rich, and as the temperature also needs to be reduced, a very fuel-rich combination is used so that the maximum temperature is not achieved well within in the nozzle. This brings down the temperature quite an extent, but still it might be insufficient in many cases. So the other method for cooling a rocket engine is ablative cooling. Ablative suggesting a very thin carbon composite layer inside the walls of the combustion chamber, where this surface actively loses a layer upon reaching a certain temperature, upon which the layer melts away and is jettisoned. So like when you have a certain load bearing capacity over here, when you see the thermal load which is happening on the surface, the carbon composite layer takes in a certain amount of heat and melts, and the surface is washed out from behind. Now a fresh layer is exposed, which is ready to take in the full blast of the temperature again. And upon reaching the temperature, this also melts away. Now, this here again, we come to a same problem as we encountered with the first cooling method of convection: thickness. The amount of carbon composite layer can only be limited to the weight a rocket can accompany. Also, the amount of thickness that has to bear. Also, we also run into certain issues, which are when you have a rocket engine, we generally see the throat section, as you can see, the throat and the exhaust section. Now, when you have a carbon composite layer, this reduces the area of throat section. So the manufacturing itself is done to accompany the best reaction to provide the maximum thrust. Now, as this carbon composite layer is washed away, it widens the throat area. Now, as this widens, the throat area is widened. Now, the expansion ratio, that is area of exit to the area of throat, is very high. Now, uh, is decreased as we tend to maintain is a high expansion ratio to provide the best thrust. Now, when we see this, this is something that we generally avoid as the rocket ascends into upper atmosphere stages. We generally maintain very strict expansion ratios. Also, as we discussed, this adds a lot of excessive weight. And most importantly, this kind of cooling method prevents the complete testing of a rocket engine. Yes, you heard it right. This method has an active layer inside the walls, which means any amount of testing the rocket, this layer is washed away. Now, as this does, the efficiency of the engine is decreased from the first burn itself. Now, one of the most famous example for this is the Lunar Ascent engine, which was used during the Apollo times. And once the astronauts landed on the surface of the moon, this engine was supposed to propel them away from the moon towards Earth. Now, this engine was never fully tested upon any of the rocket flights. Now, this also is very terrifying as a not completely tested engine is being used, as as the ablative surface needs to be protected. Now, another most common cooling methods out there that might ever have been used is the regenerative cooling, where regenerative cooling is the process where you use the active liquid coolants, where the coolants themselves are the fuels, as these are all cryogenic stages where any kind of liquid is actually only either oxygen or hydrogen or many other forms which are there. So I'm taking a general case for the simpler explanation. So now when you have liquid hydrogen and liquid oxygen, these itself are liquid at very low temperatures. Now these temperatures are very, very low, and they can also be used directly to cool the engine to a great extent. Now, as you can see, the liquid from the top section of the engine runs directly to the end of the engine, to the exhaust, and comes back. Now, what it does is it actively exchanges the heat between the fuel and the combustion chamber. Now, this draws away the heat and also increases the temperature of the fuel itself that is ready for combustion actively. Now, this is one of the most efficient methods to cool an rocket engine, as this prevents a lot of issues that we have already discussed. Now, as you can see, this regenerative cooling also comprises of a lot of things that are really interesting about it. Now, when you have a regenerative cooling system accompanied, you have active pipelines running through here. Now, what can happen is general point of failure is, as you can see, a throat section, which actually is the area is very less compared to the exhaust, is taking a great extent of the pressure and the blast of the fuels. Now, what can happen a point of failure is the one of the pipes might start leaking. So this is a very active case of a failure. So how do you counteract this? Well, as it turns out, this not we can actually ignore this point of failure to a certain extent. How? Let's discuss. Film cooling. Film cooling is another method where you separate the combustion chamber and the walls of the nozzle by introducing a new layer in between them, which takes which acts as an insulating layer between the both. Now, what can be used as an insulating layer? Well, as there are not many of the options, well, we have two as such. Well, the fuel and the oxidizer itself. Now, the most general case, what it is used is to use the fuel itself, where you take the outermost string of where this sprays pure fuel. Now, what happens is the combustion chamber doesn't have enough oxidizer in it to react for the amount of fuel that it possesses. So, the fuel in the corner closer to the wall acts as an insulator itself, where it doesn't react with anything. So, this becomes an active barrier between the both. Now, from our previous discussion, as we have seen, regenerative cooling, which carries pipes. Now, what happens is when you have a point of failure, as we discussed, near the throat section, is we have a leak. Now, when you have this fuel leaking, which is really cold, it itself starts to act as a film cooling layer. Now, this provides a very nice layer between the the flames, and the nozzle, and this provides a very active layer of cooling or insulation between the both, thus preventing the melting of a engine. Now, as many of you would have seen, one of the most brilliant form of recovering booster parts of a rocket is by SpaceX. Now, how many of you have seen this SpaceX booster landing? Well, I believe almost everyone. Well, have you ever wondered what kind of an engine it uses? What kind of process does it use to recover the booster, and what kind of mechanism it might be using? Well, if you have paid attention, this rocket booster actually uses complete liquid engine, where this has this also accompanies two certain control systems for it to help land. That is, one is the grid fin that you can see at the top of the booster. It has a hexagon pattern where it actively cuts down through the atmosphere and help reduce the speed of the rocket and to maneuver as well. Now, the other part is a little bit more tricky and way interesting. That is by using the engine itself, where the engine is actively moving to a certain degree and directing the thrust enough to counteract the differences in the balance of the booster. Now, this balances the rocket in very well situation and is able to land. This is the mechanism that it uses, that is thrust vectoring. Now, thrust vectoring is a very deep concept, and you guys can actually check out the fighter aircraft of US Air Force, that is F-35. Uses thrust vectoring to actually land and take off. Now, entering the next segment of our session, satellites. Now, satellites are categorized into many things, but let's start with the basic definition. As I mentioned earlier in our meeting, satellites are natural or man-made objects revolving another object, that's generally Earth. Now, these satellites are classified into various number of things. One of the basic things where we generally classify them is based upon the weight. And as you all must be knowing, Moon, a natural satellite, well, we definitely can't control any part of it, but it's a form of natural satellite. While man-made satellites are, as you can see, are of various forms and for various purposes. So they are classified into various categories. Firstly, coming to the weight. Now, satellites have a certain weight to them. Now, they can be as low as 1 kilogram, that is nanosatellites, to as heavy as beyond 1000 kilograms. And these are the large satellites. Now, they are in a level of progression from nanosatellites, microsatellites, mini satellites, medium satellites to large satellites. As you can see, a lot of examples as well present over here. Now, these weights range from anywhere from 1 kilogram to 1000 kilogram based upon this need of the satellite. Now, if you guys have ever imagined how these actually work, satellites travel in space. Now, as on the surface of the Earth, we have gravity to assist any kind of motion and friction, which helps us to move from one place to other for all the vehicles that or even walking. Friction is a very key essential element. Now, and it also is only in two dimensions. That's front, back, left, or right. Now, when you have an object in the orbit, by well, obviously it got there using a rocket. So when you have an object in the orbit that is beyond the atmosphere, we don't have friction, which means an object can not slow down upon its will, or as we use friction on a daily life to slow down and walk in many of the situations. So that comes the concept of orbital mechanics. Orbital mechanics is a science that deals with the motion of objects in space, basically rockets and satellites. Now, if you have noticed this diagram over here, this is something known as Hoffman transfer. Now, what is this Hoffman transfer? Now, let's just take a starting point, the green circle. Now, let's consider this is the starting point for a satellite's orbit. Whenever we have an orbit around the Earth, we can use two situations. When the satellite is at two specific points, that is apogee and perigee. Apogee is the point that is furthest away in the orbit, and perigee is the point that is closest towards the Earth, that's closer to the surface of the Earth. Now, a rocket engine can be used to produce some amount of thrust in these two situations when it's at perigee and apogee. Now, when we have our initial orbit, the green one, we generally can start based upon our end destination at any point. Now, once we start with the thrust sequence, the orbit starts to expand. The circular orbit tends to become an ellipse, while the initial point of firing, the apogee starts to increase. Now, as the apogee starts to increase, we can control to what extent it should be increased. Now, upon reaching a certain point, we can stop the burn of the engine and start the once it reaches the perigee again after we orbit, the elliptical orbit, we can wait for the satellite to move around to the next point and have another static burn. Now, as this burn starts, the perigee of the orbit starts to increase while the apogee is maintained constant. And now the elliptical orbit starts to expand, increasing the perigee to the same radius as of the apogee. Now, this again brings us to a closed circle. That's an orbit. Coming back to our violet orbit. That is the just bigger version of our green orbit. Now, depending upon where a satellite or where a spacecraft has to go, it can use numerous times this Hoffman transfer, or it can have a custom kind of a transfer sequence where it can have various different kind of burns in various different angles to travel at different locations. Now, this orbital mechanics is a very wide field where we use a lot of different mechanisms to get our precise transfer orbits. Now, as we have discussed a lot, and I also mentioned something about reaction control system. Can you guys guess what kind of an engine can this be? Well, this is a pulsed engine. So, pulsed meaning this uses short bursts of flames to direct its thrust to wherever it's required. This system is used by many of the satellites, and even if you have heard many of the capsules which deliver astronauts to the International Space Station, use this reaction control system to a great extent. The Soyuz or the space shuttle, the most famous rocket uh, ever. So these are the this plays a really crucial role in terms of any kind of object that is in orbit to control. Now, as to talk about the buildup of this engine, as you can see, these are very small thrusters. Now, from our discussion, let's just run down what kind of systems might it be using to actively cool. As the thrust it provides is for a very short burst or a pulse. The surface of the combustion chamber has enough time to actually convect the heat away, meaning we can use convection. That is our first cooling methodology that we discussed. Now, this can have enough surface to actually convect the heat away, or it can use a combination of another system, that is ablative surface. Ablative surface meaning as the surface, the top layer of the surface heats up, it melts and is carried away along the thrust. Now, which as you can see, the surface can have a certain degree of thickness as reaction control systems are used for a certain times only and for certain calculated amount. Now, the surface of this ablative surface, which is present on the combustion chamber, can actually actively heat up and wash away the top layer. Now, as it is calculated precisely for the amount of time it has to use, it decreases the weight quite a lot as it's not used in a closed cycle where it's continuously running. So that which calls for a lot of a very thick surface of ablative surfaces, and also if we are using convection, which is generally not used. So reaction control system is where we use these kind of techniques. Now, a control system, when we talk about control systems for satellites, there are two control systems that we use. That is the reaction control system, as we discussed, and for very minor movements that we all generally have for this kind of satellites all over, is the reaction wheels. Now, when we have very small motion, which needs a great precision, we can use something known as reaction wheels, which are generally used for uh, controlling very minute degree rotations. Well, these reaction wheels are come in a set of three, each for the axis, each axis. As we know, there are three axes that we use: X, Y, and Z. Now, each reaction wheel stabilizes the system in one of the respective axes. Now, when you have this reaction wheel, this spins at a great degree. Now, when this spins, this produces something known as the gyro effect. Now, with this gyro in place, this provides a great stability to the satellite or our rocket itself. Now, when we are using these kind of systems, we can actively control the satellite until the time we have power. Now, when we have a satellite, we actively have a solar panel, which is able to produce the energy that it requires. Meaning, this reaction wheels can be used for n number of times, and in most general cases where we have very small satellites, that is nanosats or microsats, use this kind of system to a great extent, as they are very small and cannot comprise the amount of fuel that they might require for the reaction control system. These play a key role in many of the nanosats and microsats. Now, as for the bigger satellites, they take fuel with them. As you guys might have heard, many of the satellites' lifespan increases very just after the launch when it reaches its parking orbit. And by parking orbit, I mean the final destination of the satellite, the final resting orbit, where it rests and also does the task that it is meant for. Now, when you have fuel, when we talk about fuel on the surface of the Earth, we generally have the fuel tanks upon certain height, which uses gravity, meaning the force that pulls it down, to actually assist in the flow of the fuel. Now, when we have gravity pulling the fuel down and directing it, we can actually actively use it. But these satellites are in orbit, meaning they experience only a fraction of the gravitational force that we generally see on the surface of the Earth. So these generally pose a challenge where we need to actively have a flow of the fuel. Now, when you see a pressurized fuel chamber, it can either be of a complete shell, or it can be in terms of a structure, as we call it baffles. Baffles are the structures which use the unique property of a fuel or a liquid, to be more specific, that is surface tension. Now, any kind of fuel that you can see or any kind of liquid in space sticks together and stays in a very nice concrete sphere, or any kind of best case scenario where the surface tension is best provided for the fuel. Now, different kind of liquids have different kind of surface tensions, but when we have a baffle is actively able to stick to the fuel, where in actually the fuel sticks to the baffles, where the baffles are generally directing the fuel towards the nozzle, towards the position where the generally the flow of fuel is required. Now, these baffles are also a great place where you guys can have an active research, where you can have more and more optimized baffles for the least amount of weight that they can have. And these baffles can be a game changer when you have the least amount of fuel, even when you have a very high amount of fuel inside a satellite. There would be certain amount of fuel left out, as the baffle cannot direct the complete amount of fuel towards the thrusters. A very best case working scenario of a baffle, which is able to direct a great extent of fuel towards the thrusters, can still be a great achievement for anyone, and a great research for area for any one of them. Now, can anyone name the costliest satellite made by humans ever? Well, guys, you can actually use the chat section for this, and you guys can take a guess. Well, yes, it's the International Space Station, costing almost $150 billion. International Space Station is one of the most costliest ever satellite out there. Well, this comprises, at least at any given point, 6 to 7 astronauts, or in certain cases beyond 10 as well, when there's an exchange of crew taking place. This marvelous piece of space station that you guys can see right now started more than 25 years ago, where building this was a great challenge on its own. And many of the things that we discussed are actively seen. And also, the most famous space vehicle of all time, space shuttle, which has which is a marvelous achievement on its own, was used for a great extent to transport many of the parts actively to the International Space Station. So this brings us to a wrap for the event. Now, as we are end towards the discussion, I we are open for Q&A. So any doubts or any questions, you guys can uh, post it in the chat section.
This marks the end of Astra. Thank you so much, Kinit, for walking us through such an exciting and informative session. On behalf of Sigma Psi, I'd like to extend my sincere gratitude to all our attentive audience for making this event a grand success. The forum is now open for a Q&A session. Please feel free to put any questions you have or unmute yourself and ask away.
Well, Mohit, well, yes, to a certain extent, ablative and film cooling are similar to a great extent, actually, to be honest. But the thing is, with ablative cooling, you have a surface actively present on the surface. Like, I'll actually go back to the slide which I used to explain. So, ablative cooling. So, as you can see, the most general case used is a carbon composite layer that is actually used to make the walls of the combustion chamber. Now, when you have a certain layer for each and every use, this ablative layer is washed away. Meaning, for each and every second that the engine runs, a surface is lost. Thus, it actually expands the throat area. Now, what happens is, as I discussed, the expansion ratio starts to decrease. As the area of throat increases, the expansion ratio decreases. Now, as you have a rocket engine which is propelling the rocket among in the atmosphere towards the atmospheric boundary or beyond. Now, we generally want to maintain this expansion ratio. But as the surface actually washes away, what happens is the expansion ratio starts to decrease, which is something that we generally don't like to have. Comparing to the film cooling, we don't have any active layer that is physically present to wash away. So what happens is we actually inject the layer continuously. So as you can see, this outermost section is actually just injecting pure fuel. Now what happens is this fuel itself creates the boundary between the walls of the combustion chamber and the flames. Now what happens is a engine can only have certain amount of oxidizer that is being carried away along. So what happens is only a certain degree of fuel is burnt away. So there's a lot of the fuel that is pure fuel which is being injected closer toward the combustion walls. So this fuel doesn't combust at all, and this actively moves away. So this carries the heat away. Now, as you noticed, generally this only works out in terms of liquid propellants. Now, what happens is this liquid propellant is actually moving along the combustion wall chamber. So this actually even goes through a phase change in general cases from liquid to vapor. And the vapor barrier itself generates a great amount of insulation as well. So these two might seem similar on the basic level, but there's a great degree of difference in terms of implementation and the use cases.
Yeah, I got it. And like another one was like you said at the first, like for blunt cones of the rocket, they have the capacity to have more temperature in the sharp cones have less temperature. Why is that so?
Um, I actually didn't get the specific point because cone in the sense like I even explained the part like blunt nose cone and a pointy nose cone, but this has a completely different role. So can you just explain your question query again?
Like which one has the capacity to like go on with high temperature?
So in general, what this actively involves a lot of aerodynamics into it. Now, in general, these two rockets which you can see, one is the PSLV and another one is a sounding rocket. Now, these two have a completely different use cases where one has to stay inside the atmosphere and one is meant to deliver a payload beyond the atmosphere. So, in general, aerodynamics of these two are used to, you know, to withstand certain degree of pressure. Now, when you have a pointy nose cone, and this kind of rockets are generally used inside the atmosphere, so it's always cutting through the atmosphere. But when you have a blunt nose cone, these kind of blunt nose cones are actively experiencing a lot of pressure. And whenever you might have heard any, rocket launches, they have a specific term that they use. The rocket has reached max Q. What do you think this might be meaning?
Like max pressure.
Right. Now that's a certain point in the atmosphere where many of the sounding rockets generally don't even approach. Where these kind of rockets actually withstand a lot of the pressure. So these blunt nose cones help in pressure with to withstand this pressure. So the temperatural role is very minute in these two. The main purpose of this is for aerodynamics.
Okay, yeah, I got it.
Yes. All right. So we have another question. Pulse-based RCS emit flame, but what about the ones emitting gas to direct satellites? Well, I'm glad that you noticed and asked this. The most generally what happens is we have two kind of control mechanisms which I discussed. Now the RCS system, as I discussed, this is actively providing a amount of thrust, but this doesn't provide enough, you know, thrust to actually change the course of a satellite. Now, what happens is a satellite also needs to reach its orbit, as we have seen, like how do they travel, but they actually use a bigger amount thruster, like one from which we discussed, like the type of engines it might be having. So it uses another form of a engine as well to actually reach its orbit, the final orbit where it has to, where it's destined to. Now, when it's trying to reach this orbit, this actually uses the same kind of fuels that are actually uh, pressurized within them. This might be in terms of liquid, like it might be liquid oxygen as the oxidizer and liquid hydrogen as the fuel. So now when you already have these two pressurized in a chamber, you might not actually again prefer a new kind of mechanism to, to go for gases or something. So it's use case dependent. It's not
It's not.
I'm sorry,
I'm sorry.
did someone
Did
unmute?
someone?
All right. So basically what happens is you might just end up having numerous amount of pressurized chambers. Like one, you have it for the fuel, that's your hydrogen. And I'm taking as an example, there are many more kind of fuels that are present out there. And oxygen, liquid oxygen in both the situation, liquid hydrogen and liquid oxygen. So you already have them pressurized in a chamber. So you might as well use the same thing to actually direct. Now this actually comes very well in hand for, space shuttle as an example, where it had thrusters at the end of it and RCS mechanisms to control as well. So it uses the same kind of fuel, but also it has a lot of load capacity. So it can use various other mechanisms as well. So basically what can happen is it can use the same fuel to actually control itself to a great extent. But when you actually see any other kind of space vehicle. Let it maybe SpaceX's Crew Dragon or Soyuz. What these two use are basically might come into the gas category, where these don't have any kind of active thrust mechanism. But what happens is they have a separate, complete different section, which is actually pushing the complete Crew Dragon module into the orbit. And the final, for just precise control when it's approaching the International Space Station, it can use this gas-based RCS to provide a very well controlled maneuverability. So what happens is it can be a combination of both, or it's just the use case dependent of how you're using, where you're using, and what purpose you're using. Yes, exactly. So like docking is a sequence where these modules finally interact with the International Space Station. And if you guys might have seen these docking procedures, there's active burst of gases which is coming out of these modules actively to correct the course towards the International Space Station. And you actually even want to control the speed as well to a great extent. So these pulses of gases or whatever it might be are actually very well calculated and calibrated. So that's when these come into play.
Yeah, Kinit, I have another question. The rockets we see, right? The main primary rockets and the other ones, the small ones beside those. What do we call those?
Well, small rockets, as in sounding rockets, you mean? Like there are a lot of categories in rockets as well. Apart from what we have discussed, this is the structural working. Now, the differentiation, as in, are you asking in from what sounding rockets and the orbital rockets, or like in general this orbital rockets itself?
Like I meant those in the SpaceX ones, like the ones that land on the ground.
All right. So now what happens is when you have a payload, well, let's just say I have to deliver a payload of about 1 ton into a certain orbit. You can use one. Let's just take an example of Falcon 9. Falcon 9 can provide engines can provide a certain degree of thrust beyond which they can't actually provide active thrust. Now if the payload is for the Falcon 9 is only limiting to 1 ton, which, well, I'm not taking the actual values are a lot different, I'm just giving an example. Now if you have a payload that has to be delivered weighing like 2 tons, 5 tons or beyond, what would happen? A single Falcon 9 would not be sufficient. So what happens is they use additional either boosters, as you might have seen GSLV, which has 2 solid boosters. So you can use additional boosters or higher powered engines to actually deliver that amount of payload into the orbit. So uh, there is a clear difference in the weight as well. So even when we deal with the boosters, which actually come back and land, they actually need to have a certain amount of fuel within them contained. So they the excess amount of fuel which they carry, that also becomes excessive weight in term while the time that's being launched, because when you are releasing the 2 sections away, like before the staging, when you are releasing the payload, the excessive fuel which is there, that's just left unburned, so that's just an extra weight that you're carrying. So the size is basically dependent on what kind of payload that you're delivering. So that's basically dependent on the weight. Like if you are just using a very small rocket, like there are many other models also which even ISRO is coming up with to deliver only specific small payloads into the orbits. So even small satellites with which can only be in like nano satellites or micro satellites, which are way less weighing, like they're not even 1 ton, they're like 10 kgs, 50 kgs or so. They can use a smaller rocket in itself, where you might be expending a lot less fuel and a lot less resources that you might have. So that's when you can see these kind of differences.
Okay, and also are the RCS used in the SpaceX landing ones for the boosters? Are those also the same thing?
It's not RCS, it's actually thrust vectoring that they use. If you notice the engine, it's actually actively, wobbling. It's actually not wobbling, it's directing the thrust. It's actually bending and curving to certain degrees. And now when you have this directing, from one angle to another, and they are very well controlled as well. So when they bend and turn, they direct the thrust in certain degree. So now this is where your guidance systems come into play, where they calculate the exact precise amount of degree that the engine has to turn to stabilize the rocket. And then they use the grid fins and a combination of this thrust vectoring to land the rocket.
Yeah, like I meant the ones at the neck. Like I know the below one is a thrust vectoring thing, but the ones that are at the neck, they correct the position, right? Before landing
Yes,
also.
like huh. So yeah, there might be some form of RCS that only uses for a single or small bursts. That's all.
Okay,
But
okay. That also is just flame only or a gas?
well, that's something that I have to look into myself. I'll get back to you on that as well.
Yeah, yeah.
Okay, so we have another question in the chat section. So satellites and ISS are in the same orbit, or ISS is below the satellites? Well, when you actually see the atmospheric breakdown, uh, I mean, the orbits in which these satellites and International Space Station are, well, they are a lot varied. And by varied, I mean, when you can see, like, I'm going to just give an example. There are different segments, different positions in which these orbits are. That's low Earth orbit, that's known as LEO. That's generally where the International Space Station is. And then we have another form of orbits, that is uh, polar orbits and geostationary orbits. Now, geostationary orbits, as the name might be suggesting, they are fixed towards the direction. So, if suppose I'm launching a satellite over India and I want it always monitoring India, so I would actually send it to a geostationary location, meaning like its orbit, the time it takes to complete its orbit is same as that the Earth takes to revolve months. So that's 24 hours. So that's where geostationary satellites come in. So each and every satellite is positioned in different heights or different zones. So they are not in the same plane at any given time. So that's how you prevent the collisions, or even one collision can result in a lot of debris. And these debris, upon accelerating and interacting with other kind of satellites, can actually bring down the whole satellite network. So it's very closely monitored and actively controlled where these satellites have to be. So they can be polar orbits, geostationary orbits, and also there is a certain region between the low Earth orbits and the geostationary orbits where the satellites actually never uh, take orbits in. That's known as Van Allen belts. Actually, you guys can check out why we don't do so. And this is actually a very nice research opportunity for you as well, where analysis of this Van Allen belts is actually being carried out actively. All right, so hoping that clears your doubt, I'll move on to the next. So flames in RCS are for orbital corrections. So what happens is you need to know the right amount of thrust that you need to provide to correct the course. Like if it's just orientation, you might just use a gaseous one, or the reaction wheels if this if you're it's a nanosite or a microsat. So what the reaction wheels itself can adjust the small deviations, but when you have bigger deviations, like the whole orbit is deviating, you might actually go back to using the fuel to correct. Now, also what happens is over the time, the satellites actually start, like, as you know, Earth is not a complete sphere. It's not a perfect sphere. So what happens? The differences in the orbit, it's also not a complete perfect circle or an ellipse. So there are a lot of differences. So over the time, the orbit starts to decay. So the orbit starts to shrink. So which is something that we don't want if you are expecting a great lifespan from a satellite. So they use these fuels to again correct their orientation and to get back the main orbit that they were positioned in. So that's when they use different kind of systems. So student organizations, as in like student groups which build rockets, I'm assuming.
Yeah, like the one called URL Space ones. I've actually seen the video. I think it's from USA. Actually, they have said that they have passed the Kármán line. Like, what exactly is it, and like, how much height is it?
So I'm not actually quite aware like how many organizations are there which have, you know, crossed the student organizations which build this actually have crossed the Kármán line, but there might be quite a few. But Kármán line, like if I'm thinking of the right thing, it's the boundary which defines the, you know, if a rocket or a satellite which is actually actively considered to enter space or something. So
Oh,
in generally that is said to be, you know, around 100 kilometers. So I think that's where yeah. So that's the boundary between, you know, the Earth and the space. So like I guess somewhere around 100 kilometers is where it's generally considered as.
okay. So like that is below the low Earth orbit only, right?
Yes, yes, yes. That's below the
Okay.
low Earth orbit. Low Earth orbits are generally more than 350 kilometers. The International Space Station itself is at 400 kilometers.
Okay. Okay. Yeah, got it. Thank you so much.
You're welcome. All right. So, any other doubts?
Now that we're coming to the end of this session, we would really appreciate any feedback you have for us so we can incorporate them into our future events. The feedback form link will be posted in the chat box soon, and the QR code of the same has been displayed on the screen. Also, everyone who has registered for 2CC, please fill in the attendance form that will be posted in the chat box as well. I'd once again like to thank all of you for joining us today. Thank you, and thank you, Kenneth, for such an exciting session. can all leave the session now. I'd like to thank all of you once again for attending.
Yeah, excuse me. The attendance will be taken automatically for non-2CC members.
Yeah, yeah.
Yes, it will.
Yeah, okay, thank you.